Look at the message. Okay, we're live on the cloud. So yeah, I'm still letting people in, but this is Zishan Lakhani. We're doing our distributed systems reading group. This is number 2 for 2023 on this paper called Distributed Reset by Anish Arora and Mohammed Gouda. I actually got this paper, I came across this paper. Does anybody here read Murat Dumas? Probably gonna say his name wrong. Murat's post. He's at AWS. Paul, I know Paul. Obviously he does. Murat works, right? Murat works at AWS. Yeah. So he had a couple papers in I would say the 2019, 2020 about like auditability and high performance systems and around reset and coordination. So this paper is was 1990. Obviously influenced things, but I've seen it a lot in papers, like as a reference for papers coming out in 2019, 2020, and a lot of distributed algorithm and system literature. So I got it from his blog post, which if I can make sure I have it here. Yeah, I have it here. He has a really good foundational distributed systems papers post. Doesn't really go into all the detail and stuff like that in terms of like why every one of them, but on this post. But he does talk. Obviously, there's a lot of good stuff here. We've read some of these as part of the distributed systems reading group previously last year. There's some classics on here. So if you get a chance to look at that, I mean, I was around at Basho when there was soon after where there is no now, Justin Sheehy one, which is really good. I mean, there's a lot of good stuff in here. You can have a whole year of reading stuff just from that post. But this came from that because actually I had not seen this one, and I thought it would be a really cool paper for us to read and kind of go into and think about, especially how to think about distributed reset for arbitrary systems. I think maybe some people here will bring about languages that might have these concepts, but and runtimes, but maybe not, in this kind of, attempt at a generic way. So I leave it open to somebody in the audience. I've been letting more people in to give a little introduction about this paper. Any volunteers? Nobody? Come on. I'll do it. Here we go.
I can't really summarize it, but is it kind of like a layer on top of the existing distributed system with waves and trying to maintain kind of a track of state and taking out cycles? Let's see. So I'm getting stuck now. So
no. I mean, it is. I think a big key in this paper is, it's a layer to work a subsystem. You could say to work with arbitrary distributed systems. That's a good thing to find. I think people maybe what I was kind of referencing earlier, maybe people who had worked in languages with runtimes and stuff like Erlang and stuff might be used to some of these concepts. Obviously, it's message passing, and they talk about that briefly toward the end of this paper. Where you have some of these paradigms kind of baked in. Obviously, certain distributed systems that are out there have some of these paradigms baked in, but it's not, it's essentially kind of a la carte in the way they kind of reference it. So that's a good point. There's some interesting stuff there about how they deal with the spanning tree. I think as Brendan's getting at, spanning tree is all things, right? Spanning tree is the definitive piece of everything, kind of running all networking. Anyone else want to kind of give a little bit of intro? That's pretty good. That's a good setup. I think it is a huge part of this paper compared to other systems.
I can give it a shot. So the paper starts with the idea that you've got some sort of distributed system, but it makes very little assumptions about it, and says, let's say that the problem you want to solve is that at a given moment, you want to bring all of the nodes of that distributed system to a predetermined known state. So that state has to be known when you set it up or when you first program it. And so you want to bring all of the nodes back to that state. So this is not consensus because you're not proposing a value during runtime. Instead, it's like consensus in that everybody passes through a state. But unlike consensus, you can't propose a value. You have to already know what the value is. So you bring everybody to that value. And then this is an algorithm for solving that problem. And the algorithm is to first construct a spanning tree with a single root so that you can distribute the it's time to reset message to all of the nodes. So I think that's interesting because you don't, if it's a distributed system, there's probably some way for the nodes to communicate with each other already, but this paper doesn't want to assume that that exists or that it's working at any particular moment. So instead it creates its own protocol. And then on top, once that spanning tree is established, you kind of bubble the it's time to reset message up to the root. The root sends, okay, let's reset as a message down through the tree to all of the leaves. And then all of the leaves bubble an acknowledgement back up to the root. And once that's done, then you know that every node has passed through the resetted state. There's no one moment where everybody's guaranteed to actually be in the resetted state, but you know that since everybody passed through that state, then any subsequent states of the system are as if everybody had once at one moment been resetted. And then I think the final key detail I would add is that you can have, I think, up to 2 resets going on simultaneously, but no more. And the way that
that's kind of an interesting question to this paper, actually. How many could you have simultaneously, even with their session index?
Yeah, I'm not clear on that, so I'd like to hear more. But whatever the guarantee is, it's enforced by saying that nodes can't talk unless they have the same session number. And a reset wave causes the session number to increment. And the session number, late in the paper, they say the session number could just be 0 or 1, which makes me think that there can only be 2 going on simultaneously, but I'm foggy.
If you want, like, I think it's in particular for like a bounded, and it's like, in a sense, you're probably, you're bounding it purposely for that, or it essentially like in a way to like just, declare that in the system. It's a good question though, if that actually works for kind of real systems or practical systems, that we actually think about. So I think that's a great question to that. So that's a great run through on this. We talked about, there's trees, there's waves. These things kind of go back and forth on how messages are sent, how things are done, and then you have this idea of sessions. As I think I have in this part right here, where you have sessions in this piece to actually kind of distinguish these waves that are coming through. And I think it's a good question. If there's how many can you actually have simultaneously? So that's really good. I think the other little thing I'll bring up too is like how to interface an application with this. There are a couple modifications that the application has to make, but essentially the ability to be able to say like I need to do a reset is one, and the ability to acknowledge that a reset is occurring, and so have that say. So there's like those small pieces which I think they talk about importantly, like you don't have to do very much to your application compared to possibly other things where you have to like involve a whole some sort of shim or another module that a whole interfacing that you have to do, which I think is pretty interesting. So it's a great roundup. I think the one part I'll highlight too before I kind of open it up too is this idea of distributed reset. They talk a little bit at the end of the paper about how this could also kind of inform or be attached to error handling, and itself being a form of distributed reset, but also these things right here to like reconfiguration, mode change, coordination loss, and periodic maintenance. Of course, upgrade seems like another case for these kind of things. So upgrading versions is always the hell of a distributed system, and kind of part of these kind of things. Like, what does it mean to actually also be reset? Brendan, please.
Just wanted to add to what you were saying, that in relation to how many resets can be happening at once, also doesn't take on the net split problem, right? And I think it's worth noting that net splits are not covered in this. I just think it's worth bringing up as like a important characteristic that the paper just pushes to the side at the beginning. Says, if you have a net split, we're not, reset's going to be, good luck.
I thought a lot too about things around like, obviously very early in the paper, they cover what is it, to have their agency, graph of nodes that are up, right? And obviously that the whole premise for the rest of the paper is the definition of understanding what is the agency nodes and like which ones are up, right? But up is wonky, right? So I think a lot about flappiness in certain systems. So if you have a constantly flapping system, what kind of happens here over time in this kind of model that's kind of trying to constantly reset, send waves down and then back up. And once you're getting all this flappiness, what happens? Like if you got constant churn this way? I used to work with a coworker, Scott Fritchie, who had a paper, one of the Erlang workshops about, this thing about humming consensus and how do you kind of understand things at a higher level around the flappiness. So that's another one that comes into play. Net split's another one too. Anyone else kind of thoughts, some of the motivations on this paper, maybe even some linking to what we think about, what do we think about distributed reset today in relation to this at a high level?
Well, I would love to talk about what we're doing. We just we're building a system that really does solve this problem in a very different way. But we also use distributed trees, and we do have an IEEE paper published about 4 years ago. But most of the new work is related to a DOI project that we're working on. Sorry, a DOE project we're working on, which is about resilience and robust computing. But that's probably not a good thing to talk about today because it will distract us from what I want to listen to about this
paper. No, I mean, I think, I think a big thing, obviously, to this point, this paper, I mean, really the kind of crux and for me, this motivation is like, how do you, in using systems today, reset is a big problem. So actually, maybe Jesse's actually asking Paul, maybe can you tell us, or a link to the work? Yeah, so you can put that in the chat. Actually, that would be really good.
Yes, certainly. We don't get our answer back from the DOE for another 10 to 12 days, so I'll put the information up on our website after that. But before that, something that's really quite important here is someone who is an expert on this particular problem, and I believe also on this paper, is Edward Lee, professor of computer science at UC Berkeley. And Ed Lee has done some really wonderful work on actors versus reactors and about these problems of ordering and about these relaxation events, this thing that you just called, I think, humming consensus and so on. Edward's a pretty good expert on all of these things. And we have him on the Clubhouse club room. It's About Time on Saturday at 9 a.m. Pacific time.
Oh, cool. Very cool. Yeah, the like actually it's not like it's a podcast essentially, right? Very cool. Yeah, so we should link to that. Everly's work is really good. I remember I've actually read, what is it, Computing Needs Time, right? That's it's like his dissertation or one of those reports, back in 2009. Very cool. Yeah, I mean, I think when I obviously kind of coming back to this paper, I would look at people's thoughts even with practical systems today, obviously having used a bunch of systems, this idea of, again, of reset, how, for me, actually, like designing these kinds of things, I've always felt like I've had to design this, even if I'm working with an existing system, I have to design this concept myself or something on top of this, right? That it's not typically as baked in as I was like, right? Obviously, there's some stuff you can do if you're using orchestration. People might think in Kubernetes land and stuff like that, you might get some of this and there's things like affinities and all this stuff that you can leverage. But, I think there's kind of an understanding of the orchestration of a system like this is kind of baked in. Does anybody have kind of any thoughts about that? I mean, obviously we can talk about too, if you felt like the paper, kind of is too generalized or has has maybe some impractical ideas. I would like to hear if people have thoughts on that, or any good stories really about self-stabilizing systems that you've been involved with. I mean, or what do people think when they think about self-stabilization today? That would be actually really interesting. Brendan, please.
Yeah, I mean, I just want to state my own bias and then reaction. Like my bias is towards peer-to-peer systems, not necessarily distributed systems. Right. And like, I find this work like highly inapplicable to the peer-to-peer context because, I mean, the definition, the leader election is going to create a natural hotspot, the sort of just natural statefulness of the whole system. And the notion that we would reset to some state is just really challenging in that context, right? And so it's
imagine like thousands of peer, you start thinking, what is the tree of 1,000 peer? I mean,
like
you could
creating
like
a rooted spanning
tree
is and then like any kind of statefulness where we're passing through what is effectively like 3 network-wide types of mutex locks is like just a very it's expensive. It's a really expensive process, and so I generally sort of what I find interesting to recognize here is the other thing that sort of jumps out is paper seems to like in the construction of the rooted spanning tree have to at bare minimum estimate the number of nodes in the network, right? Like you had this moment where you have like a k value that needs to be exceeded to detect cycles in the spanning tree.
The cycle detection. Yeah, that's right.
Yeah, and so like as soon as you have that, it's like, okay, cool. Like you have a system that has likely a monotonic counter built into the application layer. You likely have you have a need for some sort of heartbeat. Okay, cool. That's that bit I find incontroversial. But then just this addition of like a sort of 3-phased wave and a rooted spanning tree construction places a lot of that's a lot of labor in terms of network topology. That really I'd rather not pay that overhead ever and try to design the whole system to not need to arrive at any type of global state whatsoever, favoring the local knowledge approach.
Yes.
And so like I think it's really fun. This is like a fun chance to like go and look at a different neck of the woods when it comes to distributed systems where you have smaller numbers and you can do more interesting stuff because you generally, it seems like you would have full control over the system, right? Like where you have this is operating in a space where the peers are known entities and
that's actually a great point. Or even in the distributed system space, like could this work in a large kind of multi-region, multi-tenant way, or is it more like each region operates distributed reset within itself this way, but can if you want to have more like a mesh topology for the stuff, which we've seen larger distributed compute work with, obviously again thinking about locale and where things are. I mean, that puts a lot into play here. If what does it mean for like a wave to happen? Like how many processes, right? I think that brings up a lot of complication that the paper doesn't really dive into as much, right? For sure. That I agree with completely. Anyone else? Jesse.
Yeah, this is just a details question that might then be relevant to that larger question of when is this applicable. But the spanning tree at any given moment could have disconnected subnets or cycles. And if somebody starts a reset while the tree is poorly constructed that way, how does the system eventually get fixed?
Right.
how does that like reset message not end up caught in a loop or only distributed to a subnet? How do we manage the concurrency of constructing the tree and diffusing messages through the tree?
Right. So they talk. I think it's a really good question. They do talk about. I forget what page it's on. Actually, they do have a part in the paper where they try to talk about like. I think what is it here? I think it's in the like later part of the paper, right? So I guess the city stuff. I forget. It's like somewhere where they try to talk about the possible like stages that you might be in that they have to try to fix things. But that's a good question in a sense. I don't think there's like a really a firm kind of grasp on like what would happen in each of these kind of. There's no like case study scenarios, right? Which is almost kind of what you want to have in this paper is for them to take the motivations from earlier and then apply here's how this would happen in each of these different results that might occur. So that's a good question, because somebody also asked, right, what is an appropriate initial state? And I think there is this kind of thing of like, when we are in a good state to then have this process. Now, the other thing they kind of talk about, which is an interesting part of this paper, which I highlighted, which is the goal in terms of also for their proofs, right, is that they don't want to do any kind of global freezing. So you might not be in an initial state, you might be at some arbitrary state, right, which they talk about, which is actually the, I would say is showcases like a view towards something very complex to work for any arbitrary state. But what happens if things are not in a good state? When do you get back, right? That's a great question. I don't, in my mind, that's, I don't know. I will get people's thoughts on that. I have a couple ideas there, but any thoughts to that point that Jesse brought up?
So there's a major potential strategy here to solving these problems. Whenever you run into these kinds of errors, an interesting question is, can you use the notion of reversibility to undo what went wrong? In other words, to make time go backwards. Now, I'm talking about making time go backwards logically here, but that seems to be an underused strategy in computer science. And this is exactly how we solve this particular problem, which we thought about 5 years ago, maybe, or longer, on spanning trees, by the way. And the idea is that when you run into this notion of two things being symmetric, competing with each other, one of the interesting challenges is, can you identify one of them as Bob and one of them as Alice and do some kind of symmetry breaking protocol, which makes one of them back down, in other words, undo what they did, and allows the other one to continue their wave. So it's just a thought.
Right. Are there concepts like certain waves of certain resets, certain initiated resets have priority over other ones, right? Can you determine that based on anything logistically? I was actually looking at a paper in relation to this about actually resetting vector clocks, which is an interesting kind of thing as well, in terms of like, when can you actually do something like that and be safe to know that in the system, okay, actually that is a big, having worked in that, is a big reason to what people have done in the past was to get rid of obviously a lot of the space consumption that it can take for these things. But like, when can we define a state where, yeah, okay, we can kind of start over by not starting over, but knowing that we're all in a good place, right? And also, like, you mentioned a great one too, like how, when can things be definitely reversible, right? That's a great point.
So the this issue of resetting vector clocks, I'm very familiar with that paper. I'm not going to tell you where I found this out, but it's in a large infrastructure that I was involved in. We actually found out a case where vector clocks had actually been corrupted. We don't know whether it was memory or on the network, but there was an actual corruption where they thought they had a large enough vector clock, 32 bits or 64 bits. I think it was having the problem a lot at 32-bit vector lengths, but when you used 64-bit vector lengths, everyone said, well, that's so long that it's way beyond. It's 10 times or 100 times the length of time our computers are up before we replace them every 3 years. And we replace the computers every 2 years, but that's not the point. What we discovered is this corruption put the vector clock so close to the rollover point that they rolled over, and it locked up our entire system. This happened twice over in 2 years, and for the same reason. And so obviously we went hunting for all sorts of different ways to do error detection and error correction on those kind of errors. But it just goes to show you that these are major issues. And in fact, the recent work from Facebook and Google about cores being unreliable, giving different results. Right. Because of semiconductor failures, for example, potentially might have been one of the causes. So vector clocks, particularly long ones, are actually very, very dangerous. The longer they get, the more dangerous they are.
Yeah, that's for sure is a warning. Yeah, and so I mean, and this, and I think the tie-in, right, is like this, this determination of reset and the priority of reset. I mean, this comes into play, I think, all the time. I also, when I read this paper, it made me think a lot about I was a big fan, when I was working more day to day on distributed system stuff of the Dryad link stuff. Also kind of like my fascination with functional programming and working with databases. But also like all the papers around, Microsoft's Link or Dryad. I mean, the Dryad work was really, really cool. And they had a really cool distributed debugging system with Dryad. And these kind of concepts too, of like the ability to debug something, if you have a better understanding of debuggability into the system, could that help? Especially if you can automate that, can that help with self-stabilization and understanding which waves take priority? There's a lot in there as well that I think that can be kind of cross-referenced from work that's happened there and kind of distributed debugging land. That's been really cool. So anyone else kind of on that thread? So actually Lawrence brought in a question here. Yeah, implications for distributed systems, social systems, organizational resets, handling hostile takeovers. Yeah, I think this paper opens up a lot of obviously being again a little bit of its time opens up a lot of these questions. Anyone else with some thoughts, maybe more on some of the motivation stuff before, or unless we want to get more into like specific pieces of it, or other maybe things that you don't feel like are fully in there. I mean, they talk about implementation issues in the paper, but maybe not what people had in mind when they were thinking about other implementation problems. Jesse, please.
Yeah, I assume that we're passing messages between nodes, but the paper is so abstract.
Right.
I just want to point that out, that I expected at some point to say nodes pass messages to each other, but what instead we got was that they assign variables like n.i.j.
And those variables make up the entire state, right? Yeah, that's right. Yeah. They do talk about message passing toward the end, right? Like, I think that's what they're in channels essentially. And
right.
Like, that's, I think in the modern era of how we think about those things, we would be thinking much more in this direction today, right? For sure. And you're right. I mean, this is, I also think a thing of the papers in this era. They are kind of highly abstract, right? A systems paper in this vein, if you look at the stuff that actually references this paper, what you're going to get, if they're more related to like SITCOM or some of the other distributed algorithm conferences, you're going to get a full evaluation of the system, right? You're going to get a lot more that kind of deep dive into like, how did this work? How did this implementation go? Where did it falter? Here's how we're better than the XYZ system, right? That's all not here. Right. So
another random thought I had, whether or not this is the right time to bring this up, but resetting everybody to a distinguished state is kind of an application of this protocol, but this protocol could be used for a number of other things, because it seems to me that what the protocol is really doing is getting everybody to increment their session numbers, right, in the same order. Maybe up to 2 of those at a time. And then you could decide how many session numbers you want, as long as there are at least 2 or 3 of them, I think. So you could imagine you could use that to make everybody reset to a known state. But I think that they could reset to any state which is a function of the session number. So session number 5 could be different from session number 4, and that could be an interesting thing. It could be like phases of a distributed workflow or something.
Yeah, that's your point. That's interesting. Right. Yeah, and you're thinking about that like as a means for how to actually like have it where if you know these known sessions, if you have these known sessions that you can go to, like not everybody has to do it at the same time. It's like eventually for like optimizations, right? That could actually take place for this, right? In piecemeal. Yeah. Yeah, that's an interesting thing too. And I guess I mean Paul's kind of brought up like obviously building stuff now, with this thinking in mind. But I kind of wonder, anybody on this call, like who has been, when have you encountered trying to do this kind of massive state? People have worked with snapshotting, going back to certain snapshots of state. Like I kind of wonder, where people have kind of seen, like kind of had that practical motivations for thinking in this way. And to Jesse's point, I think it brings up a lot of interesting optimization points for how you might actually do this.
Distributed snapshot has had a problem with time ever since the whole concept was invented. And the thing that is most familiar here for those of you who have some connection with this is what's called a superposition in quantum mechanics. And the mathematics is absolutely identical. The concepts are identical. But sometimes the computer science community doesn't pay much attention to the quantum community, and the understanding doesn't translate very well because the terminology is different.
Right. Yeah, that's a great point.
Now, if you're interested in this, the best work that's been done on this recently has been done by the Wolfram Physics Project, where they talk about using multi-way systems, which is their mathematical equivalent of several things happening at the same time. One of them has to, be selected. That's called a multi-way system in the Wolfram rewriting system.
And actually, this brings up, obviously, rewriting systems. Term rewriting systems, obviously, like Wolfram brings up some interesting things in terms of how you would actually, possibly implement ideas like this, right? And obviously, that's something they take advantage of. It was something I learned about Wolfram stuff in particular, right? Obviously, getting into PL stuff, like how that works under the hood, is actually pretty cool. Yeah, I think that's a good point. Time and snapshots have been in conflict for a long time. Anyone else with kind of avenues this way that they thought about while reading this? Okay. Before I kind of maybe talk about a few other points, and that Paul made a lot of really good points. Kind of toward the conclusions here, I highlighted a few things. Actually, I thought there's some interesting stuff here about that they bring up other issues for like an efficient mech. So actually, they bring up, they're obviously thinking about their whole thing about, to Jesse's point about like how they deal with indexes and processes. They talk about efficiency there, but they also bring up something too, which I think is really, really insightful. A third issue is security problems involving in any application process to reset the system, right? Because obviously in this one here, an application says, "Cool, I want to initiate a reset." Now you've created essentially a wave, right? Literally, of things that might occur, and a point where things could be really complicated, maybe multiple waves, and obviously you have to have all this optimization that we're talking about maybe in place. How do we prevent certain things or certain applications from? Do applications have hierarchy here? Do applications have delegation capabilities? Like what are kind of ways that we might think of reset in that with that lens?
These are really important points. The one of the things that I really like about some of the distributed systems algorithms is when they pre-select their failover partner. And this is an old idea that goes back to tandem and process pairs, 3 or 4 decades ago. And if you can pre-select who can take over for you if you are not, if you fail, is a much more powerful technique than randomly selecting someone right. across a switched network, because you have no idea how far away they are, because all you know is their address. You don't know how many hops away they are, for example. And the more hops you have, the more likely they are likely to fail. So you don't have the topology information, you really can't select your partner.
That's right. That's right. And then how much do you have it where, this is also a thing that kind of comes up because the people who program more again in Erlang and stuff, you can actually kind of create your tree of supervision, but it's on the programmer to kind of think about the meaning of that as well when you think about some of these things. Like how much can you kind of leverage what you have in the network topology and information on the fly to kind of make no certain choices. Like this is definitely a local node that's local to this group or something like this. Yeah, any other thoughts on these kind of security implications? I know in the P2P space, right? Obviously, Brendan's on here. Like we think about that a lot. You know, and you don't want bad peers, right? And peers, you know, peers to do bad things to others. You know, obviously a reset system like this, like, you know, by attempting to put a lot of this paper is about being lax about restrictions, I think, which is a really interesting concept. They talk a lot about that. They're trying to be more lax than other, you know, obviously systems that say, hey, we're going to stop everything and do that. And I think even though they didn't kind of tackle security in this paper, what would be a lax way of doing this versus something, you know, very, you know, kind of oppressing in terms of like, well, you know, only these valid actors can ever reset stuff, so everybody else can't do anything and have to maybe you know, be thrown off or whatever the case might be. Any thoughts of that from people here? And I guess while we're doing that, people are thinking, Brandon, you had a question, right? By pre-selection. I think Paul was talking about pre-selection. Maybe Paul can answer that.
It's
Yeah,
just
go ahead, Paul.
Sorry, Paul, I don't think we heard you on the.
I'm sorry, I interrupted the other person. I apologize.
Yeah, we're having a Canadian standoff. This is great. My question was just like, how did Paul, just to get some intuition of your pre-selection, is it pre-selection prior to joining the network? Like, do you know the nodes in advance, or is it pre-selection in the sense that I join and then secretly elect, okay, based on, you know, I pick the nth peer that I come in contact with, and they're my failover buddy, and maybe I don't tell anybody that.
That's a really good question. So it really, the answer depends upon what your definition of knowledge is. And for that, you have to go deeper and say, well, what is the definition of information? And the definition of information, according to Shannon, is the answer to a yes/no question. And so that begs the question: what is knowledge and what is information? So you have to ask a question of your neighbor. And if you're going through a switch, you have complete uncertainty about how many people are beyond that switch, how big the network is, how many nodes there are out there, and so you really can't go past one hop, which is basically the hop between you and the switch, to ask a question. And the switch, unfortunately, doesn't keep this kind of information or knowledge because, by definition, switches don't keep state on behalf of applications. And so it's much better in a mesh network, where in a mesh network, you're connected directly to your neighbors, and you can know whether someone is 1 hop away or 2 hops away or 3 hops away, because it's built into your spanning tree.
And into the overlay. Yeah, right, exactly. Yeah.
So the answer to your question is, if you know the topology and you know someone's directly connected, then you can select them to be your failover partner. You know, and of course you'd have to assume that they're on a different power supply bus, rail, and that kind of thing. But in general, that's not a difficult problem. And if you just select someone who is most likely to be able to hear you when everything else is failing, then that's a good choice.
So the answer to your question is, we need overlay networks. This is brilliant. It's like the best answer I could have gotten. I have a new justification for why overlay networks are a good idea. Yeah. Thank you. I really appreciate your answer, Paul.
And I think it's to that point that the networking stuff is so important. When I was at Comcast, right, we were looking at this problem of pathfinding and source finding. And the way we did is we used like concepts like this thing called segment routing, where actually the information in that state would be packed into the packet, compressed into essentially a small array of all the possible destinations for a certain service. You would know that ahead of time, pop that into the packet, and then that packet would basically go to the switches and be like, cool, I'm ready to like be processed by, you know, node A in this region that's of the service. And it's like, oh, A is busy right now, or A is down. I already know where B is. I'm just going to go to B. Right. And then once I go to B and have and once you say, okay, now I actually have like a connection here, and now we're going to send a bunch of packets back and forth, you can then skip. The first time you have to do the whole round trip, but the second time you do it, you don't have to do any direct. We could just do direct server return. Right. So that was like a thing we built at Comcast for like this kind of route finding work. But we actually put that information in the packet, and then once we learned information about the network, the packet we can update things at switches about that information and put it back into the packet. And we had semantics use v6 for this. This was the key. The key was v6, and you know, which is still coming, right? It's still happening. but we could put messages at the end of the bits in the v6 address to do things to tell another node about like storing state or not for a connection. So we actually use like message passing in the v6 addresses. The problem is to run stuff like that, like certain things when you start getting into overlay, start getting the networking, there's a lot of cool tricks you can do, but you get into things where like certain places will look at, you're trying to do spoofing and stuff of destination addresses or something like that. So you could be a bad actor. If you have a control network, you can get away with this. If you're trying to run this in like a generalized way, then you'll run into problems. So I think, I always say it, like leveraging the network more and more and the things that it has, and like trying to build on top of that instead of building something else and trying to fit them together. Actually, it's a lot. There's a lot there, right? I think only in the last decade have you seen more networking and distributed system stuff kind of really start getting closer together, I would say. I don't know if Paul agrees with that more generally, but people are obviously the network and systems were always intertwined, but I feel like it's been a little better and like even closer in the last like decade.
No, you're absolutely correct, and that's the right way to think about it. One of the big challenges is the more you start to pack into a message, the more the longer the packets get, and the worse your latency. And so one of the interesting questions is if you were to be given a clean sheet of paper, and all you had was an Ethernet frame, which is what you have if you were talking between peers on a mesh network. Then you could actually do a whole lot more. You could actually, basically get rid of source destination addresses, which just get gigantically larger when you IPv6. And because not only do you have the MAC addresses, you also have the IP addresses, and now they're a lot larger. These are great resources to use in interesting ways, but if you use them in a legacy, everything has to be compatible. Right. Everything's the first day of Ethernet, then you're just going to make the messages.
Yeah. If you have to make it work for everybody, it becomes a bit too hard. If you have to make it work for a certain subset of things, then it works better, right? Yeah.
So but I like the idea of doing it at the end of a V6 address. We've thought about using some of the V6 address space to actually do some, I wouldn't call it message passing because we really don't like to think the applications get to touch that. We call it distributed metadata, in which case our Speckens inspired epistricted metadata is actually packed and exchanged in the IPv6 frames. And then we realized that we can make the frames a lot smaller if we just go straight to the Ethernet and get rid of the source destination addresses and use just a single tree ID, for example, with that address space.
Yeah, that's actually a great idea. And there was some tricks, NSCI, I think some years ago that Fastly was doing with some of their routing techniques to work directly on the frame information for their routers. So yeah, to that whole point, I think a lot of these kinds of ideas of thinking about optimization and how to like deal with state and information can actually be leveraged more and more by what we have in the networking already in the networking space. And that's where you said you have a lot more information than trying to kind of build something. So someone had a question here. I think it was Lawrence. Could you hash the topological space and use that as the routing method? That way you can direct a packet based on the topological shape of the route. Maybe Lawrence, you want to talk a little bit more about that question to get a higher sense of what you're asking about?
Sorry, it's maybe a naive question. I was just really curious. Sorry, you're blowing my mind in terms of like things to think about. But the idea would be like, I really like the idea of embedding, of looking at the information as an embedding problem, and looking at things around you as ways of like hallmark, basically characteristics about the environment around you that you can then encode into a small packet of information. And you can use that as a way of transferring that knowledge around. So it's kind of like landmarks in going through place to place, like look for the red stop sign, look for the green tree, look for the blue house. In a topological, in a map, in a network scenario, the characteristics that you have per node is a topological map of your interconnects for everybody in that node. So one way to route, so you can make the assumption that everybody on a particular node can look at least one hop out for what the topological map of each of the different routes are. And if they're unique enough, you could use that as a way to map assuming that the routes are consistent enough, you can map the pathway between one place to another based on the shape of the topological map. So essentially the packet wouldn't have to keep a track of each individual node. It just has to know roughly the flow of information from space to space, and the packet router would essentially look at would have basically kind of a map of where you want to go versus where you want to be, and then map not according to like a pre-described route, but the shape of the node that you're going towards. So what I'm imagining is that you'd have, like, let's say you've got a heavily connected node and at least lightly connected node. I think it'd be easy. I think where the idea falls down is that if you were trying to track between a highly connected space and a lightly connected space, you'd have to have enough uniqueness between both spaces to be able to do it. So you might have to encode more information about each individual node and what the properties are, which then gets you back to why don't you just apply a MAC address to it? So I think I might have answered my own question.
Yeah. I mean, no, that's good. I think that yeah, right. I mean, the other thing is like stuff we did, or if you're building down to the switch level, which is what we did, like a Comcast, where we built a software switch. We could essentially now then participate in BGP, and so we would know when routes were coming in and out at that level, because we would also get all the messaging that's coming from the network, right? And so obviously, I think we talk about networking distributed systems. I think the other kind of cool thing happening is there's actually a closer mix now between networking and programming languages and software engineering. So you've seen like languages like P4 has shown this with its work, but a lot of people who work on P4 now, Nate Foster and others, I'm forgetting the one big paper, the Python networking language. David Walker, it says like David Walker, Nate Foster, and all these cats and others have done a lot. And P4 has an interesting language that works on like, it's a pretty robust language to write actual like programs in that run. And if you have, if you have hardware switches that can actually run P4, you can get a lot of performance. But there's a lot of interesting things about how to work at that level and program with that, like almost like we're programming today and the web world, right? It's actually gotten so much better than it used to be, where it was like kind of just only people who knew networks could do networking things, and it's all configuration based, and there's no language and no DSLs and that kind of thing. Paul was Paul, I think you were saying that's also something you're seeing as well.
I've seen this for 2 generations or more of network engineers. Yes.
Yeah.
And that's what we're addressing too. Now, besides sending, things like, eBPF packets or fragments, to do P4 down into the NIC or into the switch, another alternative to say, well, why don't you just send fragments of Verilog down into the FPGAs? And
yes,
have
this is huge. Yeah.
Fragments and bypass an entire tool chain.
Anyway, yeah, and the FPGA thing is huge, right? I mean, that's even I was saying, larger companies. I was at a talk. Microsoft is, just hordes and hordes of huge FPGA, setups, and I think, I mean, and the programmability. There's a lot of work coming out of Cornell, and there was just recently the ASP+ conference, I think, just happened. And there's a lot of interesting work with how to program FPGAs, and do verification and much more, because actually the hard part in a lot of this is writing Verilog for a lot of people, and like how do you make that easier? And there's been some really good stories there. I think Jane Street actually has hired the person who wrote like the OCaml, OCaml tooling kind of compiler for Verilog. And they're doing that for obviously high frequency trading work, and they're running FPGAs. So you're obviously seeing where these kind of combinations are happening, which I think is really awesome. Cool. We're almost about time. Did anyone have anything else before I kind of wrap up here on the call? Cool. We got a lot of links in there. The Smart NIC Summit is a great one. Really cool run through there. Lawrence too at the end. And yeah, Brendan put his link to his videos. They're amazing. I've been saying this to everybody I work with at Fission. I actually think more people should just be like, I read actually something we should do in like my PhD reading group is like, read a paper, like actually do a video of it. And I think it actually it makes you learn a lot too, right? Presenting on papers and
stuff. And please, if anyone has a paper they think should be videoified, I'd be delighted for any leads. They take a long time to make. You actually have to like understand the paper thoroughly enough. It's the whole phenomenon of staying one lesson ahead of the student. But
yeah, for sure.
I'd love to help on some stuff we're doing. I don't know your email address. Who are you? What's your name?
Oh, on the internet, I'm B5. I'm Brendan O'Brien in Meatspace. I'm this. Oh yeah, we're just talking. So I'm assuming some robot will transcribe this, but I'm b5@n0.computer is my email. If you want to email me, I'd be delighted to chat.
n0.computer?
Yeah.
.com or .computer?
.computer. Yeah.
Nice.
Cool. Great.
They opened up .computer as a TLD, and we feel this is an underutilized resource.
Well, your earlier question was really interesting about being interested in overlays. Whether you call them overlays or underlays or whatever else is, a product issue. But there was some really great work that's done by the University of Waterloo, if you're a Canadian, by Samir Al-Kashwani and his group. And that was called partial network partitioning. I think I mentioned this in our last session a month ago.
Okay.
Awesome. Yeah.
I'd love to have a look. Thank you. And thank you, Zishan.
Hey, we're here to, I think as Lawrence said it, like we're just here to, the whole group is about to blow people's minds and find, also with that, with papers and things, what you end up finding is just more and more references. Like we are the spanning tree of more things to read, right? It's a never-ending world of practice and reading. No, cool. Thank you to everybody. Before I go, the one thing, or capturing video, Fission is we're running like a future computing conference along with Blue Yard and Protocol Labs as a sponsor. It's called Causal Islands. We'll be in Toronto in April. We just got our first 8 speakers up there. And we have 4 or 5 more getting their bios and stuff like that. So it'll be really cool. So if anyone can make it to Toronto, there's tickets and it'll be a lot of cool speakers. Maggie Appleton, Jen Schiffer, we'll have Evan Brady, Ramsey Nasser, a lot of cool people from all different backgrounds and topics kind of in the space. Cool. That's all I got. I will stop recording now. So thank you for those on the recording watching this.